2005 Canadian Open Mathematics Challenge, Part B. A line with slope -3 intersects the positive x-axis at y and the positive y-axis at b. A second line intersects the x-axis at 7, 0 and y-axis at d. The lines intersect at E, 3, 4. Find the slope of the line through CE. Well, that slope will be rise over run, which is basically the difference of the y values. So that would be 4 minus 0 over the run, which is the difference of the x values, 3 minus 7. That's 4 over -4, which is -1. So that takes care of part A. Part B, find the equation of the line through C and E and the coordinates of the point D. So we have all lines of the form y equals mx plus b. M we can find pretty easily, and we already did. It's -1. That's the equation of the line through CE, and that's the slope. So the equation is really y is equal to minus x plus b. Now to get the value for b, you just have to substitute one of those points on the line. So the equation of the line is through C and E, and we have both of those points. So I'll just use C. So that means when x is 7, y is 0. So we have -1 times 7 plus b. So therefore b is 7. So the equation of this line is y is equal to minus x plus 7. And then they want the coordinates of the point D. Well, D is on the y-axis, so that means the x-coordinate is 0. So x is 0. So when x is 0, y is equal to 7. So D is 0, 7. That takes care of B. Now we move on to part C. Part C says, find the equation of the line through A and B and the coordinates of B. Okay. Well, they told me in the beginning of the question that the slope is -3 for the line that goes through A and B. So therefore, immediately I know that y is equal to minus 3x plus b, that line right there between A and B. And then to get b, I can substitute that point because it's on that line. So when y is 4, we have minus 3x plus b. And that x value, I should have just plugged it in as 3. And then there we go. So that means b is equal to 13. So that equation is y is equal to minus 3x plus 13. And they wanted what? The coordinates of b. Okay, so coordinates of b, again, b is on the y-axis, so the x value will be 0. So when x is 0, y is 13, and therefore b is 0, 13. That takes care of C. And finally, D, determine the area of the shaded region. Okay, the area of the shaded region, we can get, I think we can get it by cutting it in half like that. And then I'll explain how I'll get it. Two triangles. So AS, area of the shaded region, will be the area of this triangle, which is OEB, plus the area of that triangle, which is OEC. OEC. And each of those, we can use length times width and all that. So, or base times height is probably a better way of describing it. So first, let's just draw these perpendiculars, that one and this one. And then you'll be able to see how we can use base times height. So this base right here, that whole distance, is really the b coordinate, so that's 13. And then this one, well, that one they already gave you was 7, so that's 7. And then this distance from here to here is 4, because that is 3, 4. And then this distance from there to there is 3. So this should be pretty straightforward. So 1/2 base times height, 13 times 3, plus 1/2 base times height, 7 times 4. So this is 39 over 2 plus 28 over 2, and that is 67 over 2. Determine all possible ordered pairs AB such that A minus B is 1 and 2A squared plus AB minus 3B squared is equal to 22. So from this, we conclude that A is equal to B plus 1, and therefore I can put that into here, this equation, substitute it. So 2A squared, but A we just concluded was B plus 1, so I'll put that in, B plus 1. Plus A, which is B plus 1, times B minus 3B squared, and that is 22. Okay, so expand this out. 2B squared plus 2B plus 1 plus, let's see here, B squared plus just B minus 3B squared is 22. So this is going to be 2b plus b minus 3b. So the b's squareds interestingly cancel out. So that's very helpful. So then I'll have 4b plus b. So that'll be 5b. And then the numbers look like 2. Yeah, just 2. So that means 5b is equal to 20. And therefore b is equal to 4. Okay? If b is equal to 4, then a is b plus 1, so 4 plus 1, so a is equal to 5. So my only ordered pair looks like 5, 4. All right, that takes care of part A. Determine all possible ordered pairs x, y, z such that x squared minus yz plus xy plus zx is 82, y squared minus zx plus xy plus yz is minus 18, and z squared minus xy plus zx plus yz is 18. Well, let's call this equation 1, let's call this equation 2, let's call this equation 3. And we obviously have to do some manipulation here. So the first thing I'm going to do is add 1 plus 2. Equation 1 plus equation 2. When I do that, I get x squared plus 2xy plus y squared is 64. A lot of stuff cancels. And then this side, in a very nice way, factors into x plus y squared. So therefore, x plus y is equal to plus or minus 8. So it works out very nicely. Then I'm going to add equation 1 with equation 3. When I do that, I get x squared plus 2zx plus z squared is equal to 100. And again, it factors out really nicely. X plus z squared is 100, and therefore x plus z is equal to plus or minus 10. So again, a very good result. And then finally, equation 2 plus equation 3. When I add those, I get y squared plus z squared plus 2yz is equal to 0. And this factors into y plus z squared is equal to 0. And therefore, y plus z is 0. And therefore, z is equal to negative y. All right, great. So that is the first part of our calculations. So let's see here. Where do we go from here? Well, if x plus z is plus or minus 10, then since z is equal to minus y, we can put that in. Minus y is plus or minus 10. So I've got x minus y is equal to plus or minus 10, and I have x plus y is equal to plus or minus 8. These two equations will allow me to solve for x and y since I've got two equations, two variables. So here we go. Let's do that. So I guess we got 4 scenarios, right? We have, let's see, 4 scenarios. I can fit those scenarios in here. 1, 2, 3, 4. The first scenario is when x minus y is equal to 10 and x plus y is equal to 8. The next scenario would be x minus y is equal to negative 10 and x plus y is still equal to 8. And then the next scenario, x minus y is equal to 10, but x plus y is equal to minus 8. And then finally, x minus y is equal to minus 10, and x plus y is equal to minus 8. Yeah, those are the scenarios. Positive, positive, negative, positive, positive, negative, negative, negative. Okay, so here we go. So with these guys, if you add them, you get 2x is 18, and therefore x is 9. If x is 9, you can sub that back into any one of these guys to get a value of y, which would be 1. And then z is equal to minus y, so z would be minus 1. So there we go. We got our first order triple, 9. Sorry, y should have been negative 1. Sorry about that. So 9, negative 1, 1. That's our first order triple without making any mistakes. Okay, so then let's move forward. If you add these two, you get 2x is equal to minus 2, and therefore x is equal to minus 1. If you substitute that x equals minus 1 into either of those, you will be able to get that y is equal to 9, and therefore z will be minus 9. So our second order triple is minus 1, 9, negative 9. Same philosophy here. We've got 2x is equal to, this time, 2. X is therefore 1. If x is 1, then that means y is minus 9, and therefore z is 9. So this one is 1, negative 9, 9. And then finally, by this point, you're an expert. You got 2x is equal to minus 18. X is equal to minus 9. Y would therefore be 1. Z is negative 1. And our final one is minus 9, 1, negative 1. So these are all of the ordered triples that satisfy the system of equations. 4 tiles identical to the one shown with a greater than b greater than 0 are arranged without overlap to form a square with a square hole in the middle. If the outer square has an area of a plus b squared, show that the inner area of the square is a minus b squared. We have to take this shape, and we are told we are given 4 of them, and then put those 4 together in a way that it forms a square. And then when you do, you'll find that inside there will be a square, a smaller square. So, I encourage you to, maybe cut this out in a paper, and then make 4 of them, and then try to arrange them. And when you do, you'll get this shape right here. As you can see, if you look at it, this is the original shape, right? And then there's just 4 of them, and they arranged it together so that it fits into a square. And that's it's a little challenging if you don't have like puzzles. It's like doing a puzzle in your mind, right? You obviously need the puzzle pieces to put them together. So I encourage you to make those pieces out of paper or cardboard or whatever. And then they're saying that this big square has an area of a plus b squared, which of course makes sense since the side length is a plus b, and the area of a square is the side length squared. Then they're saying you need to justify that this small square that's inside has an area of a minus b squared. Okay, that shouldn't be that hard to figure out. Let's label this now. This whole side from there to there was a. So that whole side was a. And then, let's see here. In this bottom piece right there, this side is b. So that is b. So I conclude that this segment is a minus b. And then since it's a square, they told you that, all the other sides are also a minus b. So the area of that small square would obviously be a minus b squared. And that's all that is for part A. Part B. Determine the smallest integer value of n for which there are prime numbers a and b such that the ratio of the area of the inner square to the area of the outer square is 1 over n. If part B is true, that means the ratio of the area of the inner circle, which is a minus b squared, over the area of the outer circle, which is a plus b squared, is 1 over n. So that's our equation. Let's take the square root of both sides, so that will just leave me with a minus b over a plus b, and that would be 1 over root n. Okay, so they told me in the question that a and b are both prime numbers. They're numbers, they're integers. So that means that a minus b is also an integer. I'll just write I for integer. So you have an integer over an integer. So that means that this is either an integer or a fraction. So one thing we do know that there's no root sign in there. There's no, square root. But there is a square root sign here. And the only way that this will be equal is if n is a perfect square. Because if it's a perfect square, then there will not be any square root once you take the square root of a perfect square. So if n is a perfect square, then that means n is equal to k squared. All right, because this has to be a non-radical. There can't be any square root because this side has no square root. Okay, so that means that a minus b over a plus b, if you substitute this guy, is equal to 1 over k. All right, and let's bring that up here. So cross multiplying, we get k times a minus b is equal to a plus b. Right? And let's see, where do we go from here? Let's expand this out. We get k a minus kb is equal to a plus b. And then I put all the a's on one side, so ka minus a, and then b, kb plus b, and then factor out the a, we get k minus 1, and factor out the b, we get k plus 1. Now, we want the smallest value for n, right? Smallest value for n. So to get the smallest value for n, smallest value of n, we need to choose the smallest value of k. So since they're integers, let's try k equals 1 and see what happens. If k equals 1, and we're really concentrating on that equation, we get 0 is equal to 2b. So therefore b is equal to 0. But that doesn't work because a and b are prime numbers. They told me that in the question. And b equals 0. 0 is not a prime. 0 is not prime number. So this didn't work. Okay, no problem. Let's keep going. Let's try k equals 2. If k equals 2, then we have, again, looking at that equation, a is equal to 3b. All right. So if a is equal to 3b, then that means a could be 3. 3 is indeed a prime number, but then that means b would be 1. And 1 is not prime. So that kind of falls apart. Okay, no problem. Keep going. Let's try k equals 3. If k equals 3, this equation here now becomes 4b is equal to, 4b is equal to 2a. So that means a is equal to 2b. Well, if we have a equal to 2, again, b would be 1, and that falls apart because 1 is not prime. Okay, we'll get there. I think we're pretty close. K equals 4, let's see. Again, in this equation, we would get 5b is equal to 3a. And here, if a, for example, was 5, b would be 3, and both of those are indeed prime. So there we go. We got a solution. That works. So that means that k equals 4 is the value that works. And since n is equal to k squared, n would be equal to 16. And this is the smallest. We can keep going, of course, k equals 5, 6, 7, but this is the smallest integer value that works for us. to make both a and b prime and to make this hold true. So there you go. N equals 16 is the answer to part A. Part C. Determine with justification all positive integers n for which there are odd integers a greater than b greater than 0 such that the ratio of the area of the inner square to the area of the outer square is 1 over n. So it looks familiar, but a few different items this time. They're odd integers this time. And those odd integers, a is greater than b is greater than 0. And the same thing as before, that a minus b squared over a plus b squared is equal to 1 over n. Same kind of story as part B previously. Okay, so the same kind of rationale that this is an integer, a minus b, and so is this. So just as before, I'll take the square root, so we have a minus b over a plus b, and this would be 1 over root n. And again, since a and b are integers, this will be an integer, and this will be an integer. So this side has to have integers. It can't have any square roots. So the only way that's possible is if n is a perfect square. Just like before, we set n equal to k squared. Now we have to concentrate on the fact that a and b are both odd. And that we're going to do a lot of odd even in this question. And odd even, that's known as parity. The parity of a number. Is it odd or is it even? So there's going to be a lot of that in this question. So I'll try not to, make it too abstract. They're both odd, right? So odd numbers are of the form 2a plus 1. So instead of using just small a, small b, I'll use 2a plus 1. Same thing with b, I'll use 2 big B plus 1. Any number of this form must be odd, no matter what you put in for values of big A, big B. So instead of small a and small b, I'll put in those into this equation. So now we have 2 big A plus 1 plus, the numerator actually will be negative. So I've got to subtract minus 2b minus 1. The denominator, I'm just adding. So it'll be 2a plus 2b plus 2. And then this will just put in that k value. So root n is going to be just k. So this boils down to just, let's see here, a minus b, because you can take out the 2 from top and bottom, and then a plus b plus 1 is equal to 1 over k. All right. And then we can conclude that if we cross multiply, k times a minus b is equal to a plus b plus 1. All right, so this is sort of our main equation. We had a main equation in the previous one. This is our main equation in this one. So now this is where we have to start talking about odd and even and all that stuff. So here we go. The first scenario is if both a and b are even. So big A and big B are both even. So if that is the case, then that means a minus b would be even. So for example, if you have 6 and 4, 6 minus 4 is 2, which is obviously even. Okay. So that means that this k times a minus b, which equals a plus b plus 1, this is even, correct? I just showed that. But then what about this guy, a plus b? If they're both even, if you have, say, 6, 4, and 1, that obviously is going to be odd. So this side is odd. Now we've got a problem, right? Because this side is even and this side is odd. But we've got a k here. What if I multiply the even side by k? Well, it doesn't matter. No matter what you multiply an even number by, it will always stay even. So if this is 6, if you multiplied it by 3, it would be 18. If you multiplied it by 4, it would be 24. It just always will be even, no matter what k is. So that means this whole side is always going to be even. And therefore, the even cannot equal odd, so that falls apart right there. So this scenario, where they're both even, is no good. So that's shown that it won't satisfy this equation. Okay, keep going. What about if you have both of them as odd? Well, if they're both odd, so we're pretty much doing the same thing, but this time we're kind of saying they're both odd. Okay, so whatever, right? Say 7 and 3. Then a minus b would be an even number. And a plus b plus 1, well, that looks like it will be odd, correct? I mean, you can verify with just some example, like 7 and 3. It would be 11, which is odd. Okay, so then, again, we have the same kind of story. Exact same story, interestingly, as here. And as you can see, it doesn't work. So this also falls apart. So no good. Okay, so then what about if one is odd and the other is even? So that perhaps could work. So let's see. So that means I'll choose, say, A is even and B is odd. Or the other one is that A is odd and B is even. Let's see what happens there. Let's just use some examples. So we'll use 8 and 5. And then same thing, 5 and 8. It makes it less abstract, makes it easier to understand. Okay, let's go back to our main equation and see what happens. So in this scenario, we got k times a minus b. A minus b, well, if this is 8 and this is 5, that's 3, so this will be odd. And then it's going to equal a plus b plus 1. Well, if it's 8 and 5 and 1, that looks to me like 14. 14 is even. So there we go. This is even. Now, can this work? Well, an odd number, if you multiply it by an even number, it will become even. So as long as k is even, it will work. Like, for example, 8 minus 5 is 3, right? 3 is odd. But if you multiply 3 by 4, it becomes 12, and 12 is even. So this is a conclusion that k must be even for this to equal. Okay, what about here? This scenario will probably have the same kind of story, I think. So we'll just do it. K times a minus b. Well, a minus b, again, is going to be even. Oh, sorry, odd. And I don't want to use these two because that's going to give us a negative. Might be a little confusing. So let me just use, I'll just use 11 instead of 5. So 11 minus 8 is 3. So again, it's odd. And then this guy, a plus b plus 1, 11, 8, 1, what's that, 20. So that's even. And then, so it's pretty much the same scenario. And we can conclude that this is only going to be possible if k is even. Okay, so we got that's a pretty good finding. So therefore, k is even, so k is of the form 2m. All even numbers are of the form 2m. But recall, n is equal to k squared. So n is k squared, so that means n is 2m squared. So all positive integers n that satisfy the conditions of the question are of this form, that n is a square of an even integer. And that's pretty much it. All n that are of that form will satisfy the condition of this question. Triangle ABC has its base on line segment PN and vertex A on line PM. Circles with centers O and Q have radii R1 and R2 respectively, are tangent to the triangle ABC externally and to each of PM and PN. Prove that the line through K and L cuts the perimeter of the triangle ABC into two equal pieces. All right. So we have to prove that we're getting sort of a semi-perimeter once you cut. So let's draw a little line through K and L like that. And then they basically are telling us that once you do, KB plus BC plus CL, that part of the perimeter, is equal to this part because it's cutting the perimeter in half. So that would be what? KA plus AL. So this is what we're trying to prove in this question. Okay. Well, we've got a lot of the tangents here because they told us these circles are tangent. So let me just draw on those tangent lines. Now, there's a rule that a lot of you know that if you have tangents and they start from a certain point, that they would be equal. So, for example, BK and BF are tangents, right? And for this small circle right here. And they are starting from B. So because they're tangents and they start from the same point, they're equal. That is a rule. So we can conclude that BK is equal to BF. And in a very similar way, you can do that again and again. So you can do that over here on this side. That's CL and CG. They're also tangents starting from C. So therefore, they are equal. CL is equal to CG. And then again, you can do that with AK and AD. This is a tangent because K is a tangent point. And this is a line that's also tangent since D is a tangent point. Both of those start from A. So therefore, AK is equal to AD. And again, you can do it with AL and AE. This is a tangent from A to L because L is the tangent point. This is a tangent from A to E because E is a tangent point. Since both of those begin at A, we conclude that AL is equal to AE. So you use that rule several times to get these equations. Okay. So now let's go back to our original equation. That is KB plus BC plus CL. And let's use these findings. KB, well, that's equal to BF. BK, KB, same thing, right? And then BC, well, BC I'll just leave for now as BC, and then CL I'll put in the CG. And when you do that, you find something interesting. BF, where's BF? BF is right here, right? BC is right here. And CG is right here. So that entire line from F to G is this. So I'll put that in. I'll just put in FG. There we go. Now let's go back to our original equation that we are trying to prove, and let's concentrate on that side. KA plus AL. And let's see if we can make any substitutions. KA or AK is equal to AD. AL is equal to AE. So AE. And then let's look at the graph here, or diagram, I should say, not a graph. AD is here and AE is here. So that whole thing is from D to E. So this is DE. Okay, so it's a pretty decent progress, I think. Now let's concentrate on this segment here, FG. FG compared to PG, because again, we're going to start looking at tangents, but let's just set it up first. FG is really PG minus PF, correct? The whole thing, PG minus PF, would give me FG. And over on this side, we can do a similar kind of equation that DE, that whole big long segment, or actually from here to here, I should say, is really just PE from P to E minus P to D. All right. Now, again, by the same sort of tangent rules, look at over here. PD will be equal to PF because D is tangent point and F is a tangent point. So since those lines are both coming from P, we can conclude that PD is equal to PF. And similarly, if you extend it all the way to E and all the way to G, it's the same story. E and G are tangent points. So PE will be equal to PG since those two lines are starting from P. So PE is equal to PG. Okay, well, if that's the case, then look what happens. FG, which is equal to PG minus PF, becomes PG is the same as PE, and PF is the same as PD. Well, PE minus PD is DE. So we just concluded that FG is equal to DE. If that is the case, then these two are equal. And those two are these guys. So therefore, KB plus BC plus CL is indeed equal to KA plus AL, which is what they wanted you to prove in part A. Part B, let T be the point of contact of BC with the circle inscribed in triangle ABC. Prove that TC times R1 plus TB times R2 is equal to the area of triangle ABC. Just to refresh your memory, if you forgot what R1 and R2 are, if you look back, R1 is the radius of the circle with center O, and R2 is the radius of the circle with center Q. Okay, so let's proceed. So here's the big diagram, and we will refer to this diagram throughout this question, and here we go. So first and foremost, let's just write what is it that we're trying to prove. We are trying to prove that TC times R1 is equal plus TB times R2 is equal to the area of triangle ABC. So triangle ABC, and that is what we have to prove in this question. So note in this diagram we have joined a few segments. We have joined I, which is the center of that circle inside ABC, to T, so we created an IT. Then we joined O, which is the center of this circle, to the tangent point K, so we created an OK. And then we, any other one, we joined O to B, so we created an OB. Okay, great. Now, note a few things here. Note that OK is perpendicular to KB, right? Because K is a tangent point, so of course it's going to be 90 degrees right there. And then also by the same principle, IT is perpendicular to BC, because IT is also going to create a 90-degree angle with BT, because T is a tangent point. So therefore, this line OB, it bisects the angle FBK, correct? because FBK is this one right here. But then since if you draw that line right there, it will cut FBK in half. So that will be the same as that. And in a very similar way, IB will bisect the angle KBC. So this line will bisect the angle KBC, which is this angle right here. It just cuts that angle in half. All right, so now let's look at angle KOB. KOB is this one. Since this is 90 degrees, KOB will be 90 minus angle OBK, or KBO, whichever way you want to say it. And therefore, since we know that KBO is half of FBK, angle FBK, we can put that in there. And then this is really just 1/2 times 180 minus angle FBK. And 180 minus angle FBK is this guy, KBC. So this is really angle KBC. And KBC, if you take half of it, you will get angle IBT, this one. So this all comes down to angle IBT. So now we created similar triangles. Now this is a very small diagram, so I'm going to draw these out a little bit bigger to illustrate what are those similar triangles. So this is K, this is O, this is B. Okay, that is 90 degrees. This one in here, I don't know, I'll just call it theta. And then this one angle is 90 minus theta. Now, in the other triangle, IBT, this small guy here, I'll draw that out, IBT. It'll be similar. This is 90 degrees because T is a tangent point. And then we concluded that KOB is equal to IBT. So since KOB I have designated as theta, IBT will also be theta. And then therefore this side is obviously going to be 90 minus theta. So there we go. I just proved, well, I showed, illustrated that these are similar triangles. So therefore triangle OKB is similar to triangle BTI. And when you have similar triangles, you can use the ratio of the sides. So that means that BK over KO is equivalent to IT over BT. And then let's see, do we have any kind of thing we can substitute? KO is R1, right? That's just the radius of that small circle. And then IT is the radius of the circle inside ABC, which they just call R. And then BT is just BT. So rearranging, I have R1 is equal to BT times BK over R. So this is my first finding. And in a very similar way, you will be able to also conclude that R2 is equal to TC times times LC all over R. So it's going to be the exact same process that I did here. I'll let you do that, but it's identical in terms of its methodology. Okay, so far so good, right? We've got some pretty concrete. And let's keep the eye on the prize here. That's what we're trying to prove. Okay. So now we move forward with these two findings. And what was our goal again? I'll put it over here on the side. That TC times R1 plus TB times R2 is equal to the area of triangle ABC. Okay. Well, let's see. Can we do anything with these findings? If I take this side here, TC times R1 plus TB times R2. R1 and R2 have got some equations, so let's substitute that in. So this would be TC times R1, which looks like BT times BK all over R. And then we have TB times R2, and R2 looks like TC times LC over R. All right. And we can factor out a bunch of stuff. TC is common to both, and so is TB, right? TB and BT, same thing. So factor out that. And then the R is also common to both. And then that just leaves BK plus LC. All right. So this is my equation 1. I'll call it equation 1. Okay. Now at this point, I'm going to start concentrating on that triangle ABC, that one that's got the circle inside of it. And I'm going to start labeling the sides. So this side I'll label as small a, this side small b, and this side small c. And remember, the perimeter would therefore be a plus b plus c, and then the semi-perimeter is a plus b plus c over 2. And you're going to use the semi-perimeter because of Heron's formula. And Heron's formula I will talk about in a minute. Let me just set it up, because you might be wondering, why is he using semi-perimeter? Well, because it has to do with Heron's formula. Okay. Now remember, these questions, part B, sort of uses part A. So if you remember question 4A that I did a few minutes ago, from 4A, we had proven that K, that whole thing, KB plus BC, you guys remember that, right? That was half the perimeter. Here, in this case, I'm calling it S. So I'll just use the same notation. So if I rearrange this a little bit, KB plus LC is S minus BC. Well, BC is A, right? That's what I called it. So let me just use those letters here. So this is S minus A. KB plus LC. Okay, great. Now I will substitute this finding back into here. And therefore, we got that TC times R1 plus TB times R2 is equal to TC times TB all over R times this BK plus LC, but that's equal to S minus A. So I'm going to put that in there. All right, so let's move this along and let's bring back that circle inside that triangle, ABC. So this was our famous triangle, and then there was that circle inside, and then we had designated that to be I, and then the tangent point T, and then these two guys, whatever you want to call them. At this point, I'll just denote them as X and Y. Right? Those are tangent points as well. So this is going to be a right angle, this is going to be a right angle, this is a right angle, like that. Okay. So again, the same sort of tangent rules. By now you're an expert, so you don't need me to talk you through it. AX would be equal to AY for the same sort of story rationale as before. BX is equal to BT, and CY is equal to CT. Okay, so the total perimeter, if you add it all up, if you add up all these guys, all of these numbers would be the perimeter. So AX plus BX plus CY plus AY plus BT plus CT. That would be all the perimeter. And the perimeter is P, and P is 2S, correct? 2 times the semi-perimeter. So S really can be any 3 of these guys. For example, it could be BT plus AY plus CY. That's perfectly legitimate. Here's BT, here's AY, and here's CY. That is legitimately half the perimeter because the other 3 guys are equal. This is equal to CY, this is equal to BT, and this is equal to AY. So I specifically chose those 3 because they're going to help us. So if we use this formula, that means that BT or TB, whatever way you want to use it, BT is the same as TB, is going to be equal to S minus that AY plus CY. Right? Well, AY plus CY is this whole side right here, which we had designated as B. So that means S minus B is TB. And in a very similarly, you can show that TC is equal to S minus C. The exact same way I showed that TB is equal to S minus B. So now let's go right back to our formula. And now we have TC, this guy, is S minus C. TB, this, is S minus B. And then we have our S minus A, and we have our R. Okay, this is looking like Heron's formula. Now, those of you who don't know what Heron's formula is, it's really easy to explain. I'll explain it down here. If you've got a triangle and you've got sides labeled A, B, and C, the area of that triangle will be equal to S times S minus A times S minus B times S minus C, all under the square root sign, where S is the semi-perimeter, A plus B plus C divided by 2. So it's starting to look familiar, right? Or similar, I should say. So that's a good thing. Okay, still got a couple more steps here. Now, if we look at this, it looks sort of similar, but we still got to add a couple things. I'm going to add an S to the top and an S to the bottom. It's perfectly allowable to do that, right? When I do that, the top becomes exactly like Heron's formula. The only difference is there's no square root. So what that really means is that it's area squared. Area of triangle ABC, all squared. Right? Because if I square both sides, that's what you'd have. The radical would disappear. And at the bottom, you've got this SR. Okay, we're getting there. Now, SR, what is that? Well, SR, just look at this triangle right there. That will help us get what is SR. And I think I can do it here without scrolling down because I want everything to stay on the same page. Triangle ABC, if you want to get the area, we can get it pretty easily with just this diagram right here. It would be 1/2 base times height. And let me just label it. This side is B, right? This side is C, and this side is A. And then we'll use these as the heights. So if you were to divide this like that, then we got 3 separate triangles, and we can use base times height. So 1/2 base times height. So base would be IY, or sorry, that's the height actually. IY, and the base is B, which is AC. Plus 1/2 base times height. The next triangle, IT, and then the base there is BC. And then 1/2 base times height, and the final triangle would be IX as the height, and the base there is AB. And then now let's use our other variables. IY, IT, and IX, those are just the radii, so that's all just going to be R. And then AC is B. Our BC is A. And then our AB is C. And then if you factor out a 1/2, if you just factor out the R, you get left with A plus B plus C all over 2. And then that means A plus B plus C over 2 is a semiperimeter, which is S. So there you go, RS. Right. So that means we showed that RS is actually equal to the area of the triangle. So here we have area of the triangle ABC all squared. And then SR is just the area of the triangle. So that leaves me with just the area of the triangle. And I think that's it. We did it. This is equal to the area of the triangle, which is what they wanted us to figure out in this very challenging and lengthy question.